To solve problems using the washer method, follow the steps below. Step 1. Identify or graph the region you are asked to revolve. Step 2. Identify the axis of revolution. Step 3. Draw a representative slice or washer and label the two radii for the outer and inner functions, in other words, capital R of x and lowercase r of x. And remember to account for any shifts if the axis of revolution is not the x or y axis. Then set up the integral formula depending on the axis of revolution. In other words, are you going to integrate with respect to x or with respect to y? And then evaluate the integral. Let's try an example. Find the volume when the region bounded by y is equal to x squared and y is equal to 2x is rotated about the x-axis. First, sketch the region with the given boundaries and visualize the rotation about the x-axis, and draw a washer to represent the revolution. So let's begin by drawing y equals x squared, which is a parabola, and y is equal to 2x, which is a line containing a slope of 2. So our graph is going to look something like this. So we can see we go through 1, 1, 2, 4, and then the slope of the line has a rise and run of 2, or a slope of 2. And we can see the region that we have here. Next, we're going to draw the washer to represent the revolution. So we're going to have to draw the outer radius and the inner radius in order to see the washer that's being created. So we have this big circular section, and we have this smaller one inside. Notice that the intersections of the two functions that bound the region occur when x is equal to 0 and x is equal to 2. Therefore, they are going to indicate the interval for the solid. In other words, our lower and upper bounds for integration are going to be 0 and 2. Since the area is being rotated around the x-axis, there's no shift. In other words, no extra area that we necessarily have to take into account. The inner radius for the solid of revolution will come from the function that is lower in the coordinate plane here, which is our parabola, y equals x squared. And the outer radius comes from our line, y equals 2x. Therefore, capital R of x, or the outer radius, is going to be 2x, and little r of x, or the inner radius, is going to be x squared. Now set up the integral and evaluate on the interval determined earlier, meaning the closed interval from 0 to 2. So for our volume, we're going to have pi times the integral from a to b of capital R of x squared minus little r of x squared, and we're going to integrate that entire function with respect to x. So if we substitute in our outer radius and inner radius, we have that for the volume, we have pi times the integral from 0 to 2 of 2x quantity squared minus x squared quantity squared. And then if we were to simplify this, it's going to end up being pi times the integral from 0 to 2 of, well, when we square 2x itself, it's going to become 4x squared, and then minus, well, x squared squared is x to the 4th, and we're going to integrate with respect to x. And when we do that, we're going to have 4x to the 3rd over 3 minus x to the 5th over 5, and we still have the pi out in front. And we're going to evaluate this from 0 to 2, and then we're going to multiply by pi at the end. If we look at our lower bound here, if we substitute 0 in, it's going to be 0. So we're going to put a minus 0 at the end. So we've got, when we substitute 2 in there, we'll get 2 to the 3rd, which is 8. 8 times 4 is 32. So that's 32 thirds minus 2 to the fifth, that's also 32. So 32 fifths. We still have the pi out in front there. Our common denominator is going to be 15, so we still have pi, and then we have 160 over 15 minus 96 over 15. And when we do the subtraction, we end up getting 64 over 15 times pi, or 64 pi over 15, which is approximately equal to 13 and about 404 thousandths. Find the volume of the solid created by rotating the region bounded by y is equal to 2x minus 1, x is equal to 4, and the x-axis around the line x is equal to negative 1. Let's begin by graphing what we're told here. So we have x equals 4 is one of the bounds. So let's draw that line in. And we have y equals 2x minus 1. That's another one. So it goes through at negative 1 and then has a slope of 2. So this line is going to look something like this. And the last bound is the x-axis. Okay. So we're going to end up taking this region that we have right here and we are going to rotate this about the line x equals negative 1. So we're going to rotate it about this. So once we sketch the original region that's over here, we can reflect it about this line x equals 1, negative 1, in order to get the other side of it and then connect it with a sequence of rings or a set of rings. And this helps us to identify the outer and inner radius functions that we have within our washer. And notice that the bounded region with respect to y goes from y equals 0 all the way up to y equals 7. And that's these values are going to be used as our lower and upper bounds of integration, or the interval used for integrating. The axis of revolution is not the x or y axis, so capital R of y and lowercase r of y need to be adjusted. The distance from the outside function x equals 4 to the axis of revolution, which is x equals negative 1, is 5 units. 2, 3, 4, 5. So therefore, capital R of y is equal to 5. The smaller radius comes from the equation y is equal to 2x minus 1. But this needs to be rewritten in terms of y. In other words, we need to solve y equals 2x minus 1 for x to put it in terms of y. And then it needs to be shifted plus 1 units to account for the revolution that's occurring about the line x is equal to negative 1. So let's first begin by solving y equals 2x minus 1 for x. So we're going to add 1 to both sides and divide by 2. So we'll end up getting that x is equal to y plus 1 divided by 2. And then if we add 1 to that at the end, we'll end up having or needing to have a common denominator. So we can rewrite this as y plus 1 over 2 plus 2 over 2, which is that value of 1, to get y plus 3 over 2. And now set up the integral and evaluate on the closed interval that we determined earlier from 0 to 7. So remember, we have the volume is equal to pi times the integral from 0 to 7, and our outer radius was 5 squared minus y plus 3 divided by 2 squared. So then if we were to square these, it'll end up becoming that v is equal to pi times the integral from 0 to 7 of 25 minus y squared plus 6y plus 9 all over 4. So then we can rewrite it again as pi times the integral from 0 to 7 of 25 minus y squared over 4 minus 6y over 4, which is 3y over 2, and then minus again 9 over 4. And again, we're going to integrate with respect to y. Now, if you wanted, you could combine 25 and subtract 9/4 from it, or you can leave them apart. Doesn't really matter. I'm going to leave them apart and just integrate each term. So we have pi, and then when we integrate, we're going to have 25y minus y to the third over 12 minus 3y squared over 4 minus 9/4 y. And we're going to evaluate this from 0 to 7. Well, if we substitute 0 in for all these y values, we're going to end up getting 0. So let's substitute our 7 in for each of these y values to evaluate. 25 times 7 is going to be 175 minus 7 cubed is 343 divided by 12 minus 3 times 7 squared is 3 times 49, which is 147 over 4. And then we have minus 9/4 times 7, which is minus 63/4. And we have all of this multiplied by pi. And again, if we substitute 0 in, we end up getting 0. So you could put a subtraction of 0 at the end of this if you would like. So if we evaluate this in a calculator, 175 minus 343 over 12 minus 147 divided by 4 minus 63 over 4, we end up getting 93.917 times pi, which is then equal to, if you evaluate it in a calculator, 295 and about 48 thousandths.